All right. So I brought some props here to maybe help me explain gases. We'll kind of see how this goes. Okay. But the thing about gases, our daughter is studying gases in high school right now, high school chemistry. I'm like, I love gases. Well, the thing about gases, they're kind of intuitive. And that means, I think anyway, when we talked, gases have a lot of space between the particles, right? And kind of because that, actually, you can take those particles and you can compress them. So one of the things I brought was this little thing. In the lab on Thursday, we're going to, in some cases, you're going to have to kind of describe what is the little chunk of gas you're talking about. So in this little demonstration, actually, is kind of bought for this. I'm going to put that plug here, so I'm going to kind of, and the gas of interest is going to be right there. So with regard to compressibility, okay, this plunger makes it airtight, okay, so our gas of interest is right there, so I could compress it. Now what do you think I'm feeling as I push down? Pressure, exactly. Yep. Yeah, they're compressed, that's all it is. Okay. The other thing about gases, I love them. They are just so wild childs. Okay, because little gas particles, they actually will, we said take on the shape of their container. Okay, they will actually fill any container you put them in. It's almost like they want to get as far apart from each other as possible. They want to explore. Okay. The other thing about gases, and it's kind of related to kind of what I'm doing here. Okay, density. If you see how dense something is, you see how compact this stuff is. Density we talked about is, we use the Greek letter rho. Okay, gosh, this is going clear back to maybe Unit 1. This is density, and what we do is we take a chunk, and we get the mass of that chunk, and we take the volume that that chunk occupies, and we do a ratio. We do a division rho. So here, as I'm doing this, I have the same mass of gas particles here, but I have a smaller volume. So I'm increasing the density. It's getting more and more and more and more dense. So when it says that it has an infinite density, that's what it's talking about. It's related to its compressibility. All right. This makes sense. And we're going to, for many of these, I have a figure to go along with them. But if you picture what a solid is, okay, so if you picture the solid particles in this wood, okay, versus the gas particles in here, okay, they're a lot more sparse here than they're here. They're packed together. So the densities of gases are low compared to solids and liquids. Gases, they're explorers. Left on their own, you can't have a pile of hydrogen gas over here and a pile of nitrogen gas over here without a boundary between them and expect them to stay segregated. They're totally going to mix this room up. Okay, mix up in this room. And the other thing is we're going to talk about one way to say what a gas is doing is to say what its pressure is. So one of the things I brought is an assortment of balloons. I haven't used these balloons for a while. Dollar Tree, right? What kind is? Okay, works. These, though, I think these are supposed to be water bombs, and they don't hold much air. But the thing is, if you inflate a balloon, okay, okay, so the thing about that gas that's in there is that gas is creating or exerting a pressure on the edges of the balloon. We're going to talk about something called atmospheric pressure of the atmosphere. And as we're walking around here, we're used to about 13 pounds per square inch hitting us in the face. Mostly nitrogen, like 80-20. 80 nitrogen, 20 oxygen. And we're just used to that, okay? So gases exert a pressure. So I have some slides to kind of talk about that. This is talking about the fact that gases are compressible. So instead of having like this sort of thing with a plunger, okay, they have chambers up there that are even fancier, right? So you can squeeze down that gas. And then what your author does is to kind of make a point. If you were to have, instead of gas, if you were to have liquid, Okay, if we were to fill this with liquid water, you think I could do that? No. Not really, not me. Maybe somebody could. Okay. Right. So gases take on the shape of their container. They are awesome. Gases are awesome. I think we should all be gases. Maybe. Not to conform, but. This one is talking about the fact that if you were to take the liquid that is in a pop container and convert it all to a gas, okay, you would need the volume of 1,700 pop cans. So over here it's a gas, and over here it's a liquid. That's what that's trying to say. So basically, if you liquefy anything, it's going to have to occupy a larger space. The problem or the reality of gases, if you take a gas that's like this much, and they're compressible, if you compress it, some of you guys know if you buy compressed air, like, you know, to use around the house or whatever, okay, compressed air will liquefy. Okay, if you take gas and make it squish together, you can actually make it become a liquid again. All right. This is talking about how it likes to mix with other particles. So we have the two colors. We have carbon dioxide and argon. I'm not sure why that second figure up there shows carbon dioxide is kind of down there at the bottom. Okay, to me it would be taking on the shape of that container. But you add argon to it and it forms a, we call that a mixture, a homogeneous mixture. Two gases in there hanging out, all squished together. And this goes back to kind of my balloon here. You know, gases exert a pressure. Okay. Almost hear it? No, you can't hear it. So when we do problems dealing with gases, whether it's this gas or whether it's this gas, let's see, oh, I brought another gas, okay, or whether it's like the gas you have in your little baster, okay, if I squeeze this, it creates a wind, okay, that gas comes out. Whatever chunk of gas you're talking about, we can fully describe that chunk of gas if we, and I draw a lot of boxes when I talk about gases, if we, here's my box that's going to contain a gas. Oops, boy, that's a terrible box. Guess it's been a while. Well, anyway, I did draw a box. Something like that. There's my container, and then these are my gas particles. Are they not adorable? And we kind of talked about the fact that gas particles, that's my kinetic energy associated with all those particles. So they're actually beating, not outside the box, but they're beating on the edge of the box. If we fully want to describe what that gas is doing, we don't have to say what those purple gas particles are, but we do need to say what pressure they're exerting against their container. We need to fully say what temperature those gas particles are hanging out at. And we need to say the volume of the container they're banging around in. And though we don't need to say the identity of the purple particles, we do need to say the number of moles. So in enters another variable. So already start to get this. Anytime you see a variable n, that is the number of moles. All right. So pressure. And this kind of makes sense. You know, if you think of those little particles as individual, the pressure that they're exerting on the latex basically is force times the area it's exerting it over, or divided by, excuse me, force divided by the area it's exerting over. Okay, so a little bit about force. A good unit of force is newtons. Okay, and newtons actually can be described in terms of kilograms, meters per second squared. Newton, not the unit, but the person, actually came up with the fact that force is related to mass and acceleration. Force is the product of mass times acceleration. So pressure then is force, which is in newtons, per area. One way to talk about area would be meters squared. Meters squared. Which is a lot. Here's meters squared. So 1 square force. So 1 unit of force in the SI system is pascals, but we don't use pascals. We use these other units of pressure. And actually the homework, if we get to it, is going to deal with these next 2 slides, just about units of pressure, units of gas pressure. So instead of pascals, we're most likely to deal in terms of atmospheres or millimeters of mercury. Notice that there is an exact relationship between these 2 pressure units. 1 atmosphere is exactly equal to 760 millimeters of mercury. And you're like, millimeters of mercury, how can that be a pressure? Well, I'll show you how that's a pressure. So this slide then shows you a whole bunch of other units of pressure. I mentioned we're walking around with, did I say 14 psi, pounds per square inch of nitrogen hitting us? I can't remember. But as we walk around this room, our bodies are used to a certain atmospheric pressure. And so up there it's 14.7. You might recognize when you guys inflate your tires. PSI, pounds per square inch. There you go. Pressure. Something practical. So here's a figure from your textbook. And this might come in handy, like I said, if we get to that homework. The way you look at these is these are all equal. So they are all at the same, they're all average air pressure at sea level. So we could pick any 2. We could pick, for instance, these 2 and set them equal. If we needed to go back and forth between pounds per square inch and atmospheres, we could say 14.7 psi, pounds per square inch, is equal to 29.92 atmospheres. If that's what we needed to go back and forth between, those units of pressure. You know, pick 2 others. If we needed to go back and forth between psi and millimeters of mercury, it would look like this. 14.7 psi is equal to 760 millimeters of mercury. That's how you can get those equivalency statements from this table. All right. So we said that gases are compressible. This is not talking about compressibility. Notice that the volume is the same. If you look at A versus B, A being the top one and B being the bottom one, does it look like there's more little molecules in B? So somebody has, I don't know how they did it, because that mason jar would be hard to kind of infuse gas particles, but somebody has put more gas particles down. Okay. And this says, basically, if you increase the number of gas particles in B, you increase the pressure. You know, and a good example is if I go ahead and go back to my balloon example, did it fall off? And I blow this up. As I take the plunger and, you know, put more, this is just air, right? It takes in air, it puts it in my balloon. Air puts in my balloon. It's pretty cool. I don't know how they thought of this. Okay? But I'm increasing the number of moles. I'm increasing N. Remember, that's the variable we use for gases. N is increasing. And we're increasing gas particles. I'm also increasing the latex volume. But at some point, that latex volume cannot increase anymore, right? So I'm increasing the pressure. Sometimes with balloons, can't you almost see that there's like more pressure in it? Like just by feeling it flappy or feeling it taut? You think it'll blow up?
Sooner or later.
It should. That was just me. I'm sorry. That was just me. It was just an experiment. Everybody's okay. You didn't even hear that bomb? That was really loud.
The alarm goes off.
She didn't even care. We could just be totally blown up in here. No one would hear.
Did you guys hear that? Okay, they didn't hear it.
Was it loud?
That was loud.
I was going to say close the door.
Yeah, next time. Okay then.
Let's get rid of the evidence.
Yeah.
So increases pressure with increasing moles, right? So the whole 760 millimeters of mercury, mmHg, the symbol for mercury. The thing about mercury, some of you guys know, is it's a liquid. Mercury's a liquid. And actually they use mercury to get a fix on pressure of the atmosphere. And here's how they do it. This is a mercury barometer. And what this gray stuff is liquid mercury. Okay, and what they do is they have a pan of liquid mercury that's open to the atmosphere. Now, then they also have a glass tube, okay, that's closed at the top. So basically what they do with that glass tube is they fill it with liquid mercury, and I kind of picture somebody putting their finger over the end and then putting it in that open pan of liquid mercury. Okay, and then what's going to happen is that liquid mercury is going to seek a level, okay, that actually is a balance between the gases that are exerting a pressure on the open container at the bottom. So as the pressure of the, have you ever heard, like if you watch the weather, sometimes the pressure's falling, sometimes the pressure's rising. Actually, that's the pressure of the gas particles. That's the nitrogen and oxygen. So if the pressure increases, the liquid mercury goes up farther. Okay, so 760 mm stands for millimeters. 760 millimeters would be 76 centimeters, right? So is that right? Yeah. 76 centimeters. 760 millimeters. Yeah, they are long. Okay. That would be how far up the mercury would travel. So anyway, that's how that works. Millimeters of mercury. So let's kind of remember the four things, and we'll talk about a few of them today. The four things that affect that box of gas, or any gas, doesn't have to be a box. Four things that affect a gas are pressure, temperature, volume, and number of moles. So here's one for you. I bet you kind of intuitively know this. As the temperature goes up, those little particles are going to move faster. As temperature goes up, the particles move faster. So actually, if the volume doesn't increase, they're going to bang harder on their container. So the pressure is going to increase. And I have a little video to show you that. So as temperature goes up, volume's fixed, could be a glass container or something, your pressure is going to increase. A good example of this is like if you buy a Mylar balloon, okay, and you, let's see what would be a good example. Let's say it's kind of underinflated when you get it from Hy-Vee. I love getting my balloons from Hy-Vee. And you take it and you put it in your car, okay, but it's nice and warm in your car. Don't you almost kind of see when you come out it's taut later? It's underinflated when you buy it, but as it heats up, those gas particles go faster and faster. Okay. Oh, here's another one. Haven't you ever, like on a hot day, had a water bottle, or even a cold day, had a water bottle and you're driving down the road and it's kind of near your heater? Your water bottle's near your heater. Haven't you ever heard kind of the plastic crinkle sometimes? Yeah. If it's sealed up, what's happening is basically those gas particles they get going faster and faster and faster. They exert a greater pressure against that container you have them in. And so it kind of uncrinkles your water bottle. So notice this. This looks like an infinity sign with a bite taken out of. I don't know if you guys have used much. This is proportional. Okay, so infinity with the bite there on the right. So we say that pressure and temperature are proportional. If one goes up, the other one goes up in proportion. Okay. We say they are directly proportional. So here is the video I'm going to show you. Oh. Okay, so N is moles, right? And actually, the thing I just did a little bit ago, I'm not going to do it again. Let's choose a different kind of food. But excuse me. As we increase the number of moles, the pressure increases. Okay, yeah. So this is assuming that the other things are constant. This is assuming that the volume and temperature are constant. So, which the volume is not constant there, right? Okay. But as I increase N, the pressure increases. We saw that with the little mason jar too. So since they have this relationship, I usually do this way. Increased number of moles, increases pressure since they're the same. We say that they're directly related, and we use the proportionality symbol like that too. Okay, so pressure is directly proportional to N. P is directly proportional to N. And I have a video hopefully for that one. Not directly proportional, but inversely proportional. So instead of going like this, inverse proportional basically is one goes up, the other goes down. Okay? So here's the deal. Here's a good example. Oh, sorry. And if that's the case, if one goes up while the other goes down, we can use the proportionality symbol, but we have to use it like this. We say that volume is proportional to 1 over pressure. That means that they have this sort of relationship, up and then down. So an example of that is, I'm not gonna blow it up. I'll just put this. Okay, so I have a certain amount of gas particles in here, and I have a certain volume, but if I were to take this volume, okay, if I take the volume and go down, can you see where the pressure is going to go up? If I take the volume, go down, that pressure is going up. Do you have a headache? Yeah, so anyway, that's my point. You can just almost feel the pressure going up. How's that? Okay. So they are inversely proportional. One goes up, the other goes down. One goes down, the other goes up. Here is showing the inverse relationship, the inverse proportionality of the two. As the volume goes up, okay, the pressure goes down. Okay, as the pressure goes up, the volume goes down. And here is the video to go with it. It's basically using that table and recognizing all numbers on that table, you can make an equality out of any pair. You can make an equivalency statement out of any pair. Okay, so let's do the first one together. Remember that you have the answers to the back of the book for the odd ones. So for this one, we need to go from millimeters of mercury to atmospheres. So what you do is you use this table and knock out, you find that 1 atmosphere is exactly equal to actually 760 millimeters of mercury. So 1 ATM is equal to 760 mmHg, the element mercury, millimeters of mercury. And then for A, we're going to go ahead and use that as a conversion factor. When we work problems converting, in this case, from 1,277 millimeters to atmospheres, remember our first term is always going to be 1,200. It's going to be the thing we want to convert from. So 1,277 millimeters of mercury over 1. And then if we use that equivalency statement as conversion factor, it looks like I can put 760 millimeters of mercury on the bottom and 1 atmosphere in the top. And that should do it. I love that factor label. So that's how you do that first one. Any questions? So they shouldn't be too bad. Okay, that's all I got.